Alrighty, ooh, that's loud. Welcome back to 105. Thank you again for joining me today. So, I've seen a lot of you have already completed Lab 0, which is great. If you haven't done it already, if you're like in the 25%-ish that haven't done it already, please go ahead and do it. Set it up while we're around to help you. Because by the weekend, people might be, trying to relax during the weekend. So try and get it done before Friday. All right, so today we get to continue our journey about learning about C. So today's topic is our variables. So as an aside, we talked a little about the hardware that makes up our computer. When we talk about memory, we're referring to RAM. That was that short-term memory we had on our machine. We also call it main memory if we want. We can access storage, like that long-term memory, stuff that is stored on your hard drive, through main memory by asking the operating system. It's not covered in this course. I will go on a little bit of a tangent near the end because that is a very useful thing to do. I'll show you how to do that towards the end of the course. But for now, we're just taking input just from the keyboard. So, how computers work is they access memory bytes. We talked about it before a little bit briefly. So computers can only store bits of information at a time. A bit, 1 or a 0, only 2 options. Not that useful. So we group them together in a unit called a byte, and it is exactly 8 bits. You should commit that to memory because it will come up every single day of your life if you are doing anything regarding computers. If we have 8 bits altogether, that means we can represent 256 different things. So that is 2 to the 8. Just like with 1 digit, that's base 10, we can represent 10 things, 0 through 9. With 2 digits, we can represent 100 things, 0 all the way to 99, right? So same idea for binary digits or bits, just the base is lower. So for a single byte, we can actually represent, if we were using whole numbers, we can represent the values 0 to 255 inclusive. So in general, if you want to use n bits to represent a whole number, it can actually represent all the values from 0 all the way up to 2 to the n minus 1 if you want to remember that, if you like math formulas. So you can plug in the number for 8 bits there to get the same answer, 0 to 255. So on your computer, every byte has its own unique address. You can think of it just like a house address. So think of it the same way. Your house, let's assume they all live on the same street. Your house or apartment or whatever has a number. Same idea for bytes in memory. So they have an address, which is just a location, which is just basically their house number. And we call memory byte addressable. So we can only access information a single byte at a time in memory. Those are just the rules of computing. So what this would look like, how we can represent this, is each address contains a byte. So some value 0 to 255. So the actual value of each byte I'll represent with that light blue background. And the value there is the current value of that byte. So it should be some value 0 to 255. So say we have, 56, 5, 0, 0, something like that. And then below that, will have an address, and their address will just be some number. So your computer has a lot of memory, so these numbers will actually get quite huge. So we might say that this byte lives at address 512,000. This byte lives at address 512,001, so on and so forth. So this would show the address and the value of all bytes. So everyone okay with that? So this is how information is represented in your computer. It's good to know this stuff since C doesn't hide that much from us. So your CPU has instructions to actually access this memory. So an instruction can read a byte from memory, so that actually retrieves that value from memory, and another instruction can write a byte to memory, or in other words, change the value of that byte, or send that value to memory if you want to think of it that way. So thankfully, you do not have to write a program that says like set the byte at address 500,000 to 24 or something like that. C will do all that for you, thankfully. In future courses, when you do more hardware, you will have to say, please set the value at this memory address, and it will be fairly tedious. So this is one of the reasons we use something like C to actually handle this for us. And this is one of the few things C actually does for us. So the number of possible addresses depends on your CPU. So you might have heard the term, I have a 64-bit CPU, or my phone has a 64-bit CPU. Pretty much every single CPU these days is a 64-bit CPU. But specifically what that means is how many bits are used for one individual address. So if I have a 64-bit CPU, that means there are 2 to the 64 possible addresses, or 18 quintillion bytes I can actually address using my CPU, which is a lot of bytes, as you might imagine. So that is kind of a ridiculous number. You would never say anything like that. Everyone here has probably bought a computer at some point, and they refer to like gigabytes and terabytes and things like that. So we typically communicate these numbers using prefixes instead. So typical prefixes we see are things like kilo, mega, and giga. So to write a byte as a unit, typically we write it as a capital B and a bit as a lowercase b. So since computers are binary machines, we also use powers of 2 for prefixes. So it's a little different than our decimal prefixes, where kilo is exactly 1,000. For computers, a kilo is actually 2 to the power of 10, or 1,024. So it's kind of close-ish, but it's not exactly the same. So 1 kilobyte is 1,024 bytes, or 2 to the power of 10 bytes. And what 1 megabyte is 1,024 kilobytes, or 2 to the power of 20 bytes. And a gigabyte is 1,024 megabytes, or 2 to the power of 30. You can go in, the next unit of this is terabyte, so terabyte would be 2 to the power of 40. So old computers, back when I was growing up, sadly enough, they were 32-bit CPUs. So since memory is byte addressable, that means it can only access 2 to the 32 bytes. And if we want to use our prefixes, we can rewrite 2 to the power of 32 as 2 to the power of 2 times 2 to the power of 30, because that's just how exponents work. I can break it up. And we now know that 2 to the power of 30 is a gigabyte. So in other words, back in my day, the old systems could only use up to 4 gigabytes of memory. So I believe, does anyone have 4 gigabytes of memory or less right now? Probably no one, right? So you couldn't use these old CPUs because it couldn't actually use all the memory you actually have on your systems nowadays. So how does this relate to C? So C uses types to describe values. So memory is just a whole bunch of bytes. One individual byte may or may not help us depending on what we're trying to represent. And remember, computers are really, really dumb. They just deal with bits and bytes, and then we as humans assign meaning to them. So what a type is in C is it tells you 2 things. It tells you what the value is supposed to represent to you as a human, and how much memory they use, because some things, well, just representing 256 different things might not be sufficient if we have large enough numbers. Might be okay for some things, might not be okay for other things. So it really depends. So the first type that we've kind of already seen in the first lecture is something called an int. So that is a type that represents an integer, so both positive and negative numbers. And in C, this is just something you have to remember, it occupies 4 bytes in total. So if it occupies 4 bytes in total, we should be able to figure out how many bits that actually needs. So 4 bytes, well, there are 8 bits in a byte, so 4 times 8 means it is 32 bits, but they both mean the exact same thing. So how do we actually represent an integer? Well, like I said before, it's 4 bytes. If we want to convert that to bits, it's just 4 times 8 bits per byte, so that's 32 bits, which would mean a single int could represent 2 to the 32 different things. So if it was a whole number, what numbers could it represent? Anyone remember that formula from like a few slides ago? And has a calculator that can do a very, very large number? Should be all the way from 0 to 2 to the 32 minus 1, right? If it was a whole number. So a single integer should be able to represent, if it was to represent a whole number, any number between 0 and what's that, 4.2 and a bit billion. So that's usually sufficient to represent any number that we'll be using for our programs, especially in this course. So how that works is see how it represents an int. Again, it's actually represented, it can actually represent negative numbers as well as positive numbers. So it uses some of those choices to represent negative values and some of those choices to represent positive values. So in actuality, an int in C represents numbers between negative 2 to the 32 and 2 to the 30, or sorry, negative 2 to the 31 and 2 to the 31 minus 1 inclusive. So if you do the math on that, that's still 2 to the 32 choices, with about half of them being negative and slightly less than half of them being positive, with the other one being 0. So how that's represented in memory is, remember what we did before? We had the ones column, the twos column, the threes column, or sorry, the ones column, the tens column, the hundreds column, so on and so forth. And then we did the same thing with binary. Well, we can do the exact same thing with binary to represent an integer. So we'll have the 2 to the power of 0 column, 2 to the power of 1, 2 to the power of 2, all the way up to the final bit, which would be represent 2 to the power of 31. So bit 0, which represents whether it's just a 1 or a 0, we call that bit 0. We give a name to it. It's called the least significant bit. And the highest bit that represents a number, which in this case would be bit 31, which matches the exponent there, is something we would call the most significant bit. So it represents the highest number we could have. So to represent a number, what we actually do, or what C actually does, is this most significant bit is called a sign bit. So we don't assign meaning to it as a number. We assign meaning to it as whether the rest of the bits represent a negative or a positive number. So if this bit is 0, it means it's unsigned. In other words of that, it doesn't have a negative. It means it's a whole number and it represents some whole number, and the remaining bits represent the whole number, and they use the exact same number columns we saw before when we argued about whole numbers before. So we use 1 bit to keep track if it's negative or positive, and the other 31 bits to keep track of the number. So the positive numbers we can represent are 0 all the way up to 2 to the 31, because we're using the other 31 bits, minus 1 inclusive. So is everyone okay with that? All right, cool. So to represent negative numbers, I'm not going to tell you how we represent negative numbers because you will learn that in another course and it can be a bit weird. All we'll know for now is that if the sign bit or most significant bit is 1, the remaining bits represent a negative number, and you won't learn what they actually mean until ECE 243. So Thankfully for us, all we need to know is how many different things an integer can represent for the purposes of this course. We don't need to know how to, interpret the bits. So here is our C program, or here's how we start a C program. Every single C program you ever write will start like this. So it will start with int main void. So what this means, again, is that main is a function that takes no inputs. That's what that void type means, so no input. And it outputs an integer, so some number that could be negative or positive that has some value between negative 2 to the power of 31 or all the way up to positive 2 to the 31 minus 1. So what we say is that right after main, we can add something called statements between the curly brackets there that the computer runs in order. So your computer is exceedingly dumb, even though you might think it is smart. It only executes in statement by statement by statement, one after the other, in the order you write them in. So they'll always be in order, no surprises. And again, that return statement, they always start with the word return and then a value that matches the function's output type. So in this case, the output type is an int, so that's why it has to return some number, and 0 is a perfectly good number, and just so happens that that represents that there's no errors with our programs. So when main finishes running, the value it outputs is a 0 in this case. And note, usually in C, every single statement ends with a semicolon. And that is because that's just the rules of C. The compiler that was created back in the day was exceedingly dumb and exceedingly simple, so you basically had to tell it when a line ended. And you'll just have to get used to it. Pretty much every statement ends with a semicolon in C. So you can declare, just another fancy word for create variables in C. So in programming languages, we have something called syntax. Basically what syntax is a set of rules that you have to follow. So in C, the rule or the syntax for declaring a variable is, you have to say the type of the variable, and then you have to give it a name, and then we have to end with a semicolon. So between these angled brackets, you don't actually type the angled brackets, you actually replace them with something. So you replace the angled brackets of type by a C type. And the only type we know for now is an integer, which is just supposed to represent a number. And name, you can call it whatever you want. The only rule is it has to start with a letter. It can't start with a number. Otherwise, C gets confused between what's a name and what's a number. So the only rule for naming it is it has to start with a letter, and then you can follow it by letters, digits, and underscores, and the name also cannot contain a space. So you can call something x1, x2, that's perfectly fine, x underscore 2, also okay, but you can't name it x space 2. So those are just the rules for naming things. So we can declare a variable called x, perfectly good variable we all know from our math class. So if we want to declare a variable in C called x that represents an integer, we would just simply type int x and then semicolon. So C would execute this line. Now there would be a variable called x that can represent an integer. So that's all well and good, but that doesn't really help us. We can't do anything that useful with it. So again, that's just declaring an integer called x. So after our program actually executes that declaration statement, C sets aside those 4 bytes to use for x somewhere in memory. Thankfully, we don't have to deal with it. We can just use x instead of using, figuring out what address this x is actually at. So if you want to get the value of x, you simply just type x, and we'll see how to do that in a little bit. But in memory, what C does, it has to store that value of X somewhere in memory, and it is 4 bytes. So what it will do is it will grab 4 bytes all together and then use that for that value of X. So it might use these addresses, so each address again is a single byte, so it might use this address ending in 4, 5, 6, 7. They'd all be grouped together, and it would use all those 4 bytes together to store that value of X. That would be 32 bits, and it would have that layout we saw before, where the most significant bit signifies whether it's positive or negative. Again, don't really have to worry about that most significant bit or anything like that. I'm just telling you, just in case you are interested. All we need to know is that that value of X is somewhere in memory and it occupies 4 bytes. So, if we want to do something interesting with our variable, like change its value to something, we can do that through something called assignment. And the syntax of an assignment statement is just name equals value and then a semicolon. So, in this case, you just replace name by that name you previously declared. If it doesn't match a name you previously declared, you're going to get an error and C is going to yell at you. We'll see that in a bit. And then on the other side of the equals is just that value, and then that needs to be a value represented by the declared type of name. So in this case, if we assign something to X, X is an integer, so we have to assign a number to it. We can't just start assigning, hello to it or something like that. And unlike mathematics, where you see X equals something and then X is always equal to that thing from now until infinity, well, unlike mathematics, you can reassign the value of a variable. So the value of X is just the last thing you assign to it, which initially might trip you up when you're first reading programs. So if we wanted to change the value of X, well, we have to do int X. That is to declare a variable called X. If you're coming from other languages, this might be weird because, well, if you're coming from Python, you don't need to do this, but in C, you have to be really explicit about everything. So here I declare an int called X, and then in the next line, I can do something like X equals to 1, and then return 0. So the rules of C are exceedingly weird. So if I just do int X, the rules of C is that at this line, so if I tried to use X or anything like that, X has a random value that is undefined that you do not know what it is, so you can't trust its value whatsoever. All that's doing is setting aside some space to actually store that X. It doesn't actually assign a value to it. So we need to assign a value to it by doing something like X equals 1. So now, as soon as we do X equals 1, our program now knows that X has the value of 1 from this point on. Everyone all right with that? Yeah. Yeah, so that's our next question. Can I declare and assign it on the same line? Because this seems like a pain in the butt. And the answer to that is yes. So you can do assignment as part of the variable declaration. If you don't want to write 2 lines, typically this is what you do. So there is more syntax we can use or another rule to do them both at the same time on the same line or in the same statement. So instead of doing 2 statements, I could do type name equals value, just all in a single line. And that statement is going to create a variable and assign to it something we call an initial value. So that is the first value that variable has. So it's just another fancy name. We like giving fancy names to things. So whenever you see initial value, that's just the first value that variable has. Also, if you want to be fancy and speak like a software engineer, you would also call this initialization. So I initialized it to 1, or I set the value to something. So other types in C that we will be using in this course, one's called a char. We have to shorten everything for some reason. Char is short for character, which is supposed to represent something on a US keyboard. Again, C started off as being very simple and US centric. So a character represents letters, digits, punctuation, something called white space, and control characters. So what white space is are like spaces, the tab characters, return characters, anything that kind of modifies text. And control characters would be something, you know, more fancy like shift and alt and all that stuff. So these control characters, you can't see them on your screen, but they do something. For instance, like tab moves text over a little bit, return goes to the next line, things like that. In C, a char type is always 1 byte, so it can represent 256 different things. So, char values are a bit weird. We haven't seen them yet. So the rules of char values in C is that they start and end with a single quote character. So a char, again, is only a single character. If I give you an example of a declaration, I can do something like char, so that's our new type. I can give it the name C, and I can give it the value A. So the value A would be between single quote characters. So this would represent something just called, you know, variable called C that is equal to the character uppercase A. We also need to represent invisible characters. They're called non-printable characters, so it's not something you could see on our screen. What C does is their rules for showing non-printable characters is they prefix them with a backslash, followed by another character that we need to look up. So this backslash is something called an escape character that tells C we're breaking the normal rules. So it's not a character we can print. Interpret this as something else. I'm going to break the rules for a bit. So there's a link here for Wikipedia if you want to see all of the special rules. But here are a few ones for you. So I could create a variable called tab that represents a tab character. To represent tab, it's just \T. Way to remember it is T is short for tab. A new line, which represents an enter, is \N. This is also called a return character. If I want to represent a backslash, annoyingly, I have to type backslash twice to be like, the first backslash is an escape character, and then I give it another backslash as like, no, just kidding, I really meant a backslash character. And then if you want to represent a single quote, you also have to escape that. So I can't write just 3 single quotes altogether. I would have to write single quote to represent the start of the character, then backslash, being like I'm breaking the rules, then a single quote, be like, no, I really actually meant just the quote character, and then the quote character to end it off, which is a bit weird, but that's how I would have to represent a single quote as a character in C. So, weird thing about C is we can also interpret char as a whole number if we want. Remember, someone just gave meaning to all the numbers to represent different characters, like A was 65. So still is a byte. We can interpret that byte however we want. So a byte still can represent a whole number between 0 and 255. If we wanted to, we could interpret that character as a whole number. Again, some value between 0 and 255. Which number corresponds to which character is defined in something called ASCII, which is the American standard for characters for information exchange or something like that. Oh, wait, I have it on the slide. Okay, I was close enough. So, boring name. If you look up or go to something like ASCIItable.com, that will show you for each character what number it represents. And the way computer works is just everyone agrees that a capital A means 65. So ASCII also only uses 7 bits to represent characters because, well, it only needs to represent 128 things. So the most significant bit of that byte is always 0. So ASCII actually corresponds to the characters or the numbers in the range 0 to 127 because it's only 7 bits. So again, you can look up these values on ASCIItable.com. printing non-English characters is out of scope for this course because, of course, there is more languages than just English. And also, yeah. So, other things we can represent in C is, well, we can have another type called a double. So that represents a number with a decimal point. So integers have to be integers. They can't have a decimal point. If we want a decimal point, we have to use the type called double. And a double is 8 bytes. It is double the size of an integer. So that's one way you can remember it. The reason why it's really called a double is because there's also a less precise type called a float that also lets you represent numbers with decimals in it, and that is 4 bytes. But it's less precise. We're going to use a double in this course, which is double the size of a float. So it's always 8 bytes. So you'll learn about how they're represented in binary again in later courses in 243. Beyond the scope of this course, we don't care how it's represented in memory. We don't care what each individual byte means. All we need to know is that it can represent a number with decimals. So for example, if we want to represent pi, we could declare some variable with the name pi of the type double, and then we can type something like 3.1415 blah, 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 and that's a perfectly good thing we can do. The last type we will use in this course, so this is the last type we'll use in this course, is something called a Boolean. So the type, again, C has to shorten everything just because, and they shorten it to bool. So a bool can only take one of 2 values, either true or false. So in practice, this only takes 1 bit, right? It's either true or false, 1 or 0. But in C, because we use memory, the smallest unit we have is a byte, so a bool takes up a byte of space. In some situations, even though it has the same space as a character, it might lead to a faster program. So the rule is, if you only need to represent something that is true or false, you should use a Boolean. So by default, you can't use the bool type unless you add this hashtag include angle bracket std bool.h to the beginning of your code. And then after that, you can use the type bool and use the values true and false. So for example, we could declare a bool. Usually you call it something that can either be true or false, like it kind of answers a question. So I could create a Boolean called is snowing that is currently, unfortunately, equal to true. So, which should signify that it currently is snowing. So, all the previous types except for that bool are enabled by default. So the default built-in to C types are something called primitive types. Just basically means you can use them without doing anything special. And in this course, for now, we will only use int, char, double, and bool. There's some other built-in types that are kind of derivative of these. We'll see them more soon. For now, just worry about these 4 ones. So unfortunately, there's not too much like committing to memory in this course, but this is probably something you will have to commit to memory in this course, the different types and what they can represent. We'll also learn how to create our own types later in this course, which will be fun, but these are the main ones for now. All right, shifting gears a little bit to how we actually develop software so we can represent it as a bit of a diagram. So usually how we develop software is we edit our code, so we edit our C file, and then we make some changes. We try to compile it. So we compile it. We'll either get a yes or a no from the compiler, whether or not we can compile it. So if we cannot compile it and the compiler says no, well, it gives us something called a compile time error. So there's some error whenever we try to compile a program, and it will give us an error that we will have to fix. We'll go back to edit our code to try and fix that error, and then compile it again. And if we haven't screwed up, it should now correctly compile. Now we have our executable that we can run. So now after we compile, we would try to run our executable and then run it and see if we get the correct result. If we do not get the correct result or something really bad happens, that's something called a runtime error. So some issue happened when I tried to run my program. And then if that happens, I get some type of error, something bad happens, I have to go back, edit my code, try and fix it, recompile it, hopefully it compiles, try and run it again, and then now check to see if this is correct. If it is now correct, we are done, and you probably followed something like this if you have already done Lab 0, but this is pretty much your life now. So get used to it. This will be your life, at least for this course. So hopefully you don't have to go around the loop a lot of times. So hopefully it's just compile yes, run yes, boom, you're done, and then you go home happy, or you're already at home. So compile time errors, it means we can't create our program, we can't actually run anything because it's not created yet. So let us have a little example. We will create some issues. So this is a program that I showed before where we declare an X and then we try to assign a value to it. If we try to compile this, well, it says no work to do. It gives no errors. Errors will be in red text. It will start screaming at us. So this means it's a yes. We could run this. Turns out this program doesn't actually do anything, but there's no actual errors if we try and run this. If we try to introduce an error to see, a compile time error, what I could do is something like this. So if I change x equals 1 above int x, I can already start noticing some bad things going wrong. So one bad thing going wrong without even trying to recompile anything is there's this little red underscore under x, which red underlines are bad. They indicate some type of error. So if I hover over it, it says use of an undeclared identifier x. So that's something you can see in your IDE. If for some reason you didn't see that underscore, you will see it if you tried to compile your program. So if I try to compile it, it will do something like this. It will say failed, yell at me, and then give me some things. This line is like how you actually compile it. If you followed Lab 0, we showed you how to use Clang to compile something, and it looked really simple. This command looks very complicated, and that's why we use the compile command, because, well, we actually add a few options that do some extra stuff that you don't need to worry about. The first thing we should be able to read is this line. So what this line is trying to tell us is that there is an error in this C file. So this C file matches the name of the file that I'm currently trying to compile. I called it undefined-xc. So the first thing it's saying that there is a problem with this file. Then it gives me a colon and then a number and then a colon and then a number. What this means is that the first number here is the line number. So that 4 indicates that there is a problem on line 4. And you can see here, this is line 4 in my editor. So that means there is some issue here. And it happens to be pointing me directly at that red underlined X there. And 5 is the column number. So if I count the number of characters over, it's like space, 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 and X starts at character 5. So this is telling me what character is. Generally, you can just ignore that second number. The arrow will point you where you need to be directing. Then it says error, and then it gives you a fairly cryptic compiler message. So this one says use of undeclared identifier X. Basically what this means is the compiler read your program from top to bottom, and when it read it from top to bottom, it did this line, then this line, then this line, and this was okay. Then it read this line and then tried to use X. And remember, X equals 1 is I'm trying to assign a value to X. And the rules of C is that X actually has to exist. So if I look up, does X exist? In this scenario, no, because it only exists below it. So C is dumb. It doesn't look into the future. It only looks above it. So in this case, X doesn't exist. So that's what this error means. Use of undeclared identifier X in more plain English means I don't know what the hell X is. You didn't tell me what it is. You might have told me later, but I don't read later. I only read one line at a time. So this means I don't know what X is, and then it points you at the X, says, I don't know what the hell this is. And when you hover over that underline, you get the exact same error message there, just in line. So you'll get yelled at it in two places. So this would mean I have a compile time error. If I need to fix this and get rid of the error, the solution is I just have to move int X up one line, right? So if I just move it up one line, I can do something like this, compile it, and now I don't have any compiler messages whatsoever. And then another thing I can do too is, before I had return 0, but now X is also an integer. So instead of returning that value 0, I can actually return that value X and return a different number from my program and use a variable. So I can compile that, and actually when I run this now, I can actually see the number here comes from whatever main had. So in this case, I set it equal to 1, indicates something's wrong with my program. Remember, by convention, you should return 0 if nothing is wrong, and some non-zero value if there is some problem. So it's trying to tell me that there's some problem with my program because it returned a 1, but I was just being weird about it and returned a 1. If I wanted to change it, instead of returning just 0, I could change the value of X to something like 0. Then if I recompile my program and I run it, it just now runs normally. I don't see this 1 at all. Everything is hunky-dory. So any questions, anything we want me to do? I usually reserve about 10 minutes at the end of my lectures for any questions, so we can go through, play with code, and do a whole bunch of fun things. In this case, we don't actually know enough to do anything fun, so we can take this extra 10 minutes and we can leave early, and I will hang around just in case you have any other questions. So just